So, have you ever been in a problem where you are given an array and you have some operation in which you have to repeatedly find the maximum uh, in an interval or in the entire array, and then maximum or minimum, and then result of that operation affects the entire left or entire right or some region of the array, and the order remains and the order is not disturbed in these type of scenarios. So we usually think in these manners in these type of questions of like RMQ or sparse tables. But there's also another data structure called Cartesian tree, which is an hybrid structure which inhibits the post-order traversal. Means feature means when we traverse it in post-order fashion, we'll get the original array, and uh, and also the heap and the heap function, like the node is always strictly greater or less than uh, whichever we are using the function, then our the children's. So yeah, this type of structure is called the Cartesian tree. Yeah, it inhibits both property, like in order property, like traversing, we get the array, and in post order, in order, sorry, whatever, and the heap property is like the node is always greater than or less than their children. So what happens is that in our node, the node is always greater, and all the elements that are smaller than our node on the left side will go to the left subtree, and those in the right side will go to the right subtree. And to make this, we use this a monotonic stack to keep a record of the largest or the smallest element, whatever we are dealing with. Uh, so for this example, we are going to be a max heap structure. So we use this stack because it holds the rightmost path. Current rightmost path is keep held uh, at the stack, and whenever we get something that is not in this path, so we add it, and accordingly change the uh, stack elements. So with this decision made, like we get an input element AI, we check that if AI is greater than whatever we have at the back of the our stack, on the top of the stack. If it is not, if it is not greater than that, so it means that stack top is nearest largest, so AI becomes the right side because it's coming after that element previously in the stack. So it becomes the part of the right side of the that whatever in the top. And if it is greater than whatever in our stack currently, so means that stack on the top is small, and that element moves to the left subtree of AI. So that's how we generate it, like this. Yeah, we get an AI, left AI is last, so it means that the last element popped is the left subtree, root of the left subtree, because it's the smallest number just before our index I, element on the index I. And similarly for right child, that comes stack isn't empty, and if we, yeah, pop the elements and stack is not empty, the correct top is the nearest largest value to the left. So yeah, it becomes the right, so our I becomes the right child of the currently top element. So here's the initialization. First element is 9. So we store 9 because the stack contains the current rightmost part in the case of maximum. Um, so it contains 9. We push it. Here is the structure. Now comes 3. 3 is on the right side of the 9 and is less than. So we just add it to the right side, to the stack, and it becomes the right subtree. And now comes the 7. Since 7 is greater than 3, so while we emptying, popping out the stack, it's not empty till the end. So we add, so it becomes, so evidently 7 becomes the right child of 9, and 3 becomes its left child. And comes 1, and 1 is smaller than 7, so it just stacks over it in the stack, and we get 1 as the right child of the 7, and here is the final Cartesian tree. So this process is simple. We take the largest element, put it there, and then we go to the right side. If it's not greater than our current element, whichever it is in the stack top, so we just make its right side because it's the rightmost smaller, uh, right, not rightmost, leftmost in the right side of that element that is smaller than it. So it becomes the root of the right subtree. And if it is greater, so we just pop out things. And if the stack is empty, then it becomes the root. And if it's not empty, so it becomes the uh, left side of the current, whatever node, whatever value is on the stack top. So yeah, that's how we construct a Cartesian tree.